This is really kind of the last topic that can be considered review from what you've learned in previous classes here. And what we are going to talk about today is resistor combination techniques. So let's first consider resistors in series. So let's say that we have several resistors in series. Let's call this guy R1. This guy R2. And this guy R sub n, so that we are representing a combination of n resistances in series. And let us suppose that there is a voltage drop V across this series combination of resistors. Because all of the elements are connected in series, we know that they share a common current, I, flowing through all of the resistors. Okay? Ohm's law tells us that there will be a voltage drop over resistor R1 due to the current flowing through that resistor, which I'm going to call VR1. And I am arbitrarily choosing the current to flow into the positive polarity terminal. We are going to have a voltage drop over resistor R2, which I will call VR2. And we will have subsequent voltage drops over all of our resistors in series, ending with a voltage drop VRN, like so. Applying Kirchhoff's voltage law around this loop, what we find is that V, the total voltage drop, is simply the sum of VR1 plus VR2 plus all of our voltage drops up to VRN. We can now express all of those resistor voltage drops in terms of that common current I that's flowing through all of those resistors, which would give us I times R1 plus I times R2 all the way out to I times Rn. And if we factor out the common term I, this just becomes I times R1 plus R2 all the way out to R sub n, or I times REQ, comma S, the equivalent resistance seen by that voltage V on the left. So from this, we can say that REQ sub S is simply R1 plus R2 all the way out to R sub n, or using summation notation, the equivalent resistance when we have resistors in series is simply the sum from I is equal to 1 all the way to n of R sub I. So this is a long mathematical description for something that you all already know. Resistors in series just add directly. Okay. We've just formalized that description by applying our circuital law. Now let's talk about resistors in parallel. Right. So let's say that we have a network containing a multitude of resistors connected in parallel, where we'll call this resistor R sub 1, this resistor R sub 2, and again, this resistor R sub n. They are connected like so. And let's say that there is some known amount of current I flowing into this resistor network, which will subsequently split off and some portion will flow through each of these resistors. So that I can say this current is IR1, this current is IR2, and this current is IRN. Since all of these elements are connected in parallel, we know they share a common voltage, which we'll simply label V. Okay? So if we apply Kirchhoff's current law at that top node where currents flowing in equal current flowing out, what that gives us is I, our total current flowing into the resistor network, is simply the sum of IR1 plus IR2 all the way out to IRN. We can express each of these resistor currents in terms of our voltage V using Ohm's law. So that's going to be V divided by R1 plus V divided by R2 plus V divided by R sub n. If we factor out the common term V, we are left with 1 over R1 plus 1 over R2 plus 1 over R sub n, or V divided by REQ, comma P, so an equivalent resistance of all of our resistors in parallel. From this relationship, we can see that REQ, comma P is 1 over R1 plus 1 over R2 plus 1 over Rn, and the reciprocal of this sum, or in summation notation, 1 divided by the sum from I is equal to 1 to n of 1 over R sub I. So this tells us how we combine resistors in parallel. Now there's a special case for resistors in parallel where we don't have to do this annoying the sum of the reciprocals and then we take the reciprocal out. Okay. So let's say that we have exactly 2 resistors in parallel. Let's call it R1 and R2 like so. our equivalent resistance based on what I've just derived is 1 over R1 plus 1 over R2. We all okay with that? What I'm going to do is I'm going to multiply R1, or the 1 over R1 term, by a factor of R2 over R2. So this is the same as R2 over R2 times 1 over R1 here in my denominator. And I'm going to multiply my 1 over R2 term by a factor of R1 over R1. What this gives me is 1 over R2 divided by R1 times R2 plus R1 over R1 times R2. Since my fractions in the denominator have the same denominator, the denominator of the denominator is the same. I know that's odd sounding. I can combine those two fractions together, which gives me 1 over R1 plus R2 divided by R1 times R2, which is the same as R1 times R2 over R1 plus R2. I'm explicitly showing you this representation of how to combine two resistors in parallel because I find that it's significantly more quick to do it this way. So I often express two resistors in parallel using this method. Okay. So I just want you to know where it comes from when I use it, because I'm going to use it a whole heck of a lot in this class. All right, so how do you guys feel about this? Again, largely should be reviewed, right? What I would like to do now, yes.
Does this only work for 2 resistors in parallel, or can it do 3?
Fantastic question. It only works for 2 resistors in parallel, okay?
Gotcha.
Let's talk about why just real quick, okay? So if we had 3 resistors in parallel and we tried to apply this method, REQ, does that equal R1 times R2 times R3 over R1 plus R2 plus R3? The answer is no, and we can tell that just by looking at the units, right? So dimensionally, this is going to look like ohms cubed divided by ohms, which is ohms squared, which is not the unit of resistance. Okay. We could do a more rigorous mathematical proof, but I think that this is actually sufficient to prove that it can only be done using 2 resistors. Now, if you had 3 resistors in parallel, what you could do is combine 2 of these resistors using this method that I've detailed here, and then combine the 3rd resistance with the equivalent resistance previously so that you're splitting it up into groupings of 2 resistors that you're combining, and you can do that all day long. So if we had R1 in parallel with R2 in parallel with R3, this is the same as R1 in parallel with R2 times R3 over R2 plus R3, which in turn has an equivalent resistance of R1, my stylus will write, times R2, R3 divided by R2 plus R3 over R1 plus R2, R3 over R2 plus R3. Where all I've done is use that two resistor combination method twice to get that result. Yes. I don't know. The short answer is because I didn't teach 120 last year. Because there's a lot of stuff in circuits 1 that I taught in 120 and they stopped doing it for whatever reason. I can't tell you what it is. Things like current voltage, well, current division less so because you guys don't really use current sources, but the concept of voltage division is a very, very powerful analysis tool that we're going to learn literally Friday. And it's a pretty fantastic way of figuring out what voltage drops are in a circuit with multiple resistors in series where you never have to bother calculating a current. It's not particularly difficult to understand. It's actually almost identical derivations to what we did today. But for whatever reason, they stopped teaching it in the 120 series. They apparently don't do the R1 times R2 over R1 plus R2 method either, which seems crazy to me because it's so simple. The only potential drawback there is that it's only applicable for exactly 2 resistors in parallel. But you can make it work by just combining 2 resistors and making your network smaller and smaller and smaller iteratively. So, anywho, talk to Dr. Corbett. She's the one in charge. Tell her Dr. Hartman says to make the circuits part more fast. Yeah, it's ridiculous. It's entirely unnecessary. I feel that that's much more confusing than doing this method, which is why I teach this method. There's a couple of things that I teach a little bit differently than the other circuits teachers, even when we talk about current division, which will also be coming up on Friday. The method that most professors teach is technically only applicable for 2 resistors in parallel. The way I teach it, it is applicable for an infinite number of resistors in parallel. I feel that my version is much better because it works for all cases, but hey, I am a very conceited jackass, so I always think my way is better. All right, so the last thing that I want to do today is I'm going to open up WebWork. We are going to look at a resistor combination problem that's probably a little bit more difficult than what you are used to seeing in your previous classes. And I want to use this as an example of how I personally carry out my resistor combination problems. This is the one. Okay. So in this particular problem, we are given values for resistors, all that kind of good stuff. The hard part here is really how it's drawn. And so I'm going to talk to you about how we could simplify something like this. In order to carry that out, I'm going to need to redraw this circuit. So we have a resistor here, a resistor here. I believe there is a diagonal resistance here, a resistance here, a resistance here, and then let me just double check, but I believe this exact configuration is mirrored about that axis, and I'm correct. All right. So I'm going to go ahead and give all of these things numbers. So let's see, there's a 100, a 25, $50 ohm, 200, 75 ohm. And then let's see, R2 has a value of 145, R4 has a value of 74, 145 and 74. R1 is 86 and R3 is 280. So 86 and 280. And then lastly, I'm going to label my terminals. So they call this C, B, A, if I'm not mistaken, yeah, a D down here. All right, so in part A of this problem, we are asked to find the equivalent resistance looking in through terminals A and B. In part B, we are asked to find it looking in through terminals A and D. In part C, we're asked to find the equivalent resistance looking in through terminals B and D. All of these are going to give us different results. I'm only going to work one, and I'm going to allow you to choose. So do you want me to work part A, part B, or part C? They're all of roughly equal difficulty, and they will all illustrate what I'm trying to show pretty equally. So it's an arbitrary decision. Several people saying B, let's rock and roll with B. So in B, we are asked to find the equivalent resistance seen between terminals A and D, okay? So R, A, D is our quantity of interest. So whenever I have one of these problems, which involves what I would consider to be non-trivial resistor combination, the first thing that I do is I identify all of my nodes and I label all of my nodes. Whoever wrote this problem has been nice enough to give us labels for some. I'm going to go ahead and label and identify all of them. So let's call this guy out here on the right node A, which I've labeled in red. This guy here is B. This guy over here is C. This guy down here is D. This guy on the left, I'm going to call E. And this guy on the right, I'm going to call F. I personally prefer to use different colors for this because that helps me see which elements are connected in series, which are connected in parallel, and all that kind of good stuff. Okay. So what I do for a problem like this is if we're trying to find the resistance AD in this case, I put node A on the left-hand side of my page, and I put node D on the right-hand side of my page. What I'm trying to do here is I'm trying to stretch out and kind of unravel this circuit to see what the connections are. And I'm going to do that effectively by playing connect the dots like I'm a 5-year-old, just using resistors, okay? So, for example, if I want to go from node A to node D, all I'm doing is just figuring out all of the different resistive paths that make that happen. So we can see by inspection that there is a path directly from node A to node D through the 280 ohm resistor. So that's the one I'm going to start with. The most simple path is where I'll start. we all okay with that? Another thing that I'm going to do here is I'm going to put a check mark by the 280 ohm resistor in my original drawing to let me know I've already included that one in my redrawing of the circuit. Now, an alternative path that we could take would be to go from A to D through node F. So I am going to put node F here, if my stylus will allow me to draw, in the middle of my circuit. And I know that I can go from A to F through my 75 ohm resistor. And I can go from F to D through my 200 ohm resistor. Are we all okay with that? Again, I'm just going to put a little check mark by my 75 ohm and my 200 ohms to remind myself that I don't need to include these in my drawing anymore because they're already in it. Now, a different path is I could go from A to B to D. Right? So I'm going to put B here, also in the middle. And to go from A to B, I would go through the 86 ohm resistor. And to go from B to D directly, I would go through the 50 ohm resistor. And what is going on with my computer that's making the screen jump around like a maniac? All right, so I'm going to put a check mark by my 86 and my 50. Okay, so now we've effectively exhausted all of the paths that originate at A. But we can notice that when we go from A to B, there are multiple branching paths off of B that will eventually lead us to node D as well. So we have to take care of those. So we could go from B to C. So I'm going to put node C right here. And my path from B to C is through the 145 ohm resistor. And from C, I can go directly to D through the 74 ohm resistor. Or from C, I can go through E, which would include the 100 ohm resistor. And then from E to D is the 25 ohm resistor. And if I'm not mistaken, those are all of my resistors. So from here, it's fairly easy to see what steps we would need to take to combine to get our equivalent resistance, right? So the first thing that we can see, let's just start from the bottom and work our way to the top, right? That 100 ohm resistor is in series with the 25 ohm resistor. Are we all okay with that assumption? It's not really an assumption, actually, observation, right? So we could replace those two resistors with a single 125 ohm resistor. We can obviously see now the 74 ohm resistor is in parallel with that 125 ohm resistor. So that's just going to be 74 times 125 over 74 plus 125, or a 46.482 ohm resistor. One thing that I want to point out here, it may not be intuitively obvious what I'm doing, but if I see two resistances between nodes C and D in parallel, I'm replacing it with a single resistance between nodes C and D. Okay? So I can delete this path and then call this guy right here 46.482. Obviously now the 145 ohm resistor is in series with that. So I can replace my resistance between B and D with a 191.482. This is obviously in parallel with the 50 ohm resistor. Which looks like 39.647. Now I have 39.647 in series with 86. That looks like 125.647. I have 75 in series with 200, which obviously looks like 275. I finally have those three resistances in parallel. So that's going to look like 1 over 280 plus 1 over 275 plus 1 over 125.647. And then I just take the reciprocal of that sum of fractions, giving me an RAD value of 65.934. I've been doing these resistor combinations things as part of circuits 1, circuits 2, and other classes and all that kind of jazz for literally years at this point, and this is still the method that I rely on to this day if I can't look at it and say, well, that's how this is going to simplify. So I find this to be a particularly powerful method. And again, I like to use different colors because that helps me kind of map everything out and just make sure how things are supposed to be connected. So I'm trying to impart my skills to you. Colby.
Scroll down just a tad so I can see the. Thank you.
So that is all that I wanted to talk about today. We do have a mini lab assignment that will literally just involve using a multimeter to measure resistances for a particular combination of resistances. There is an in-class assignment, excuse me, as well. I'd like to pull that up just momentarily to give you guys a hint as to how I feel that one is more easily solved.
Dr. Hartman,
Ma'am.
what do the people at home do for the mini labs?
So,
Or is it just an L?
it is not just an L at all. For this particular mini lab, literally, if you have a breadboard, a multimeter, and the resistors that you need, you can do it at home. There is no piece of equipment in this room is required to do it.
Okay.
So you can do it at home if you have all of that stuff. If you don't happen to have all of that stuff, there is a day set aside at the end of the quarter for any student who misses any mini labs for any reason to come and make them up. The due date for the mini labs, I'm ostensibly going to put it as, you know, the class meeting prior to our next meeting. So this mini lab will officially be due on Friday. Unofficially, it's due at the end of the quarter. I'm not going to penalize anybody for doing any of the mini labs late. It's a participation grade. So if you did it, you participated. So if you don't want to do it today, You're free to do it some other time. Doesn't hurt my feelings in any way, shape, or form.
Okay. I know that before class today, there was a mini lab 2 that was supposed to be due, but I know that for our last meeting,
That's literally we're doing today, and I
Oh.
haven't gotten around to assigning the thing correctly
okay,
or
gotcha.
setting up the submission portal correctly, because I thought we were doing it on Monday.
Yeah.
Informed me we were not, and I was like, well, okay. So I just have to get off my lazy butt and change the submission date, which I think Nathaniel emailed me about, and then I never got around to doing it. So
Okay.
I will do it shortly.
Thank you.
No problem. All right. Sorry for making you guys look at my horrifying Dropbox with all my crazy classes. Let's see. I think this has a PDF of the in-class assignment. In-class assignment number 3. Okay. So just as a very, very brief thing here. In this problem, I'm asking you to find the resistance between terminals A and B, terminals A and C, and terminals D and E. The first step that you should take is to combine the thing that I've circled here on the right-hand side, because that's going to show up in every single thing and it's not going to change. So find the equivalent resistance of that first, and then just treat that as a single resistor for all of your subsequent analysis, and that will make the problem much, much easier to do. Okay. All right, so with that, I am done talking.